Hey, this is Kat, and I'm here to talk about molecule polarity with you today. So, we've already talked about the polarity of bonds, which we know is based on an uneven distribution of electrons in the bond, which is related to electronegativity. When we talk about the polarity of a molecule in its entirety, we also have to consider the distribution of electrons. So, we want to look at a couple examples, okay? When we are talking about a polar molecule, we are going to say that the electron distribution is not symmetrical and that this type of molecule is going to have a dipole, okay, which is a slight positive / negative charge due to the electron arrangement. Okay, just like we do with positive and negative dipoles within a bond, we're going to show those with our lowercase delta, slightly positive, slightly negative. Okay, nonpolar molecules, just like nonpolar bonds, have an equal distribution of electrons. So any imbalance in charge is going to cancel out. Okay, equal distribution of electrons, charge cancels out, no dipole. Okay, let's take a look at a couple of examples of some different molecules. Okay, so I've got 3 different examples of a polar molecule, and what you can see here is not only the Lewis structure / molecular geometry, but I've also got some symbols that are going to indicate what that dipole is. So if we've got HCl that we're looking at first, you can see that we've got hydrogen with no lone pairs of electrons, chlorine with a large number of lone pairs, 3 lone pairs, 6 electrons, and that's going to give that chlorine the slight negative charge in the dipole, hydrogen slight positive, okay, based on that unequal distribution of electrons. Okay, notice this little symbol here. Okay, that's a symbol for a dipole. We're not going to use those. We're just going to use the slight positive or negative. But if you notice that arrow, it's got a positive on the left-hand end, and then the arrow points towards negative. That's how you would see a dipole arrow used. Okay, second example for a polar molecule is ammonia. We can see that lone pair of electrons on the nitrogen. That's going to give that a slight negative, and we would say that these hydrogens would all be slightly positive. Okay, so you can see those arrows pointing towards the nitrogen to show where that negatively charged dipole would be. Okay, finally, we've got CH3Cl. We've got 3 lone pairs of electrons on the chlorine. It's got a nice high electronegativity, making it slightly negative. In this case, we've got a slight positive on the carbon because that's where our polar bond is. Okay, so we can still see that negative dipole on the carbon chlorine bond, giving the molecule overall an unequal or asymmetrical distribution of electrons. Okay, looking at our 3 nonpolar examples, these all have lone pairs of electrons on our terminal atoms or outside atoms. The difference in these examples is that the molecule overall is going to have a symmetrical distribution of electrons. And so that's going to cancel out any of those polar bonds that we see and those slight charges in the bonds. So when we look at BF3, we can see the 3 fluorines, each with 3 lone pairs. We have to consider our geometry as well. So if we look at our center atom for boron, we have 3 bonding regions. We have 0 lone pairs. So this is going to give us a trigonal planar geometry. Okay, and that's going to be symmetrical, right? That would be a flat molecule. That's what planar means. Okay, and so all of those fluorines would be equally spaced around the bromine, making that symmetrical and nonpolar. Okay, when we look at this CCl4, that's carbon tetrachloride. Again, those chlorine carbon bonds are all going to be polar. And so we could actually, and that's probably a good thing to do, is mark that with our slight negatives and slight positive on the carbon in the center. I'm gonna go ahead and back into doing that with our bromine and not bromine, our boron fluorine bonds in this one as well. Okay, but we can see that that tetrahedral geometry that we get in the carbon from 4 bonding regions and 0 lone pairs on the carbon. Okay, it's going to wind up giving us a symmetrical arrangement of our electron density. Okay, so all of those chlorines are going to be equally spaced. They're equally pulling the negative charge towards the chlorine. That's going to be nonpolar. Okay, let's look at some examples as to how we would build our Lewis structure, talk about geometry, apply polarity, and then just kind of go through this process with some real examples. So we actually just looked at ammonia, and so I'm going to go ahead and skip that one as far as the Lewis structure, since we already have that one up here. Actually, you know what? I'll just go ahead and do it real fast. So we've got NH3 with our lone pair. Okay, we've got 3 bonding regions and 1 lone pair, which means this is going to be trigonal pyramidal or trigonal pyramid. When we look at our molecules, we take a look at this up here. We definitely do have polar bonds, right? I already marked them, and that's going to be our nitrogen-hydrogen bonds. So we're going to mark this here. Okay, yes, and that's our NH bonds. Right, so I'm going to go ahead, let me switch colors and mark that polarity. Okay, in my structure I just drew, slight positive on our hydrogens. Okay, does the molecule have lone pairs on the center atom? Yes. Okay, are lone pairs and polar bonds symmetric? No, they are not, which is going to make this molecule polar, right? We've got more electron density around the nitrogen, so we've got more negative charge on that end of our molecule. Okay, let's look at Cl2. Okay, we've got 2 fluorines with 7 valence electrons apiece, which means we've got 14 to use. I'm going to go ahead and do that chlorine-chlorine bond. There's 2, 4, 6, 8, 10, 12, 14 electrons. We're all set. Everything's got 8 valence electrons surrounding it. We've got 1 bonding region and 3 lone pairs on our chlorines. Okay, so regardless of how many lone pairs you have, if you have 1 bonding region, this is linear. Okay, do we have any polar bonds? No. Okay, chlorine-chlorine, equal in electronegativity. They're going to have an equal pull on the electrons in the shared bond from each chlorine nucleus. Okay, do we have lone pairs on the center atom? Yes, we do. 3 lone pairs on each. Are they symmetric? Well, yeah, that chlorine-chlorine is perfectly symmetrical if we cut it down the middle. Okay, yes, it is symmetric, which means this is going to be non-polar. Okay, there is not one piece of that Cl2 molecule that is going to have a greater electron density or an unequal electron distribution, making that molecule nonpolar overall. Okay, let's look at CH2O. We're going to count up our number of valence electrons. 4 from carbon, 2 hydrogens at 1 apiece, 6 electrons from oxygen. That's going to give me a total of 12 valence electrons to use. Okay. Carbon's listed first. There's only 1 of them, and it's lowest in electronegativity. So that's going to be, those are all going to be cues that that's going to be our center atom. Okay, I'm going to put my hydrogens around, put my oxygen there. That's only 3 electron pairs, or a total of 6. I've got 3 more that I need to use. So I know that hydrogen is going to have a full valence shell with only 2 electrons. So I don't want to do anything else to the hydrogens. I'm going to go ahead and put my remaining electron pairs as lone pairs, starting around the oxygen, start on the outside and then move in. And then I want to check valence. So we already said hydrogens are taken care of. Great. Okay, oxygen, if I take a look at that, I've got 2, 4, 6, 8. That's a full valence shell for oxygen. Oxygen's looking good. Okay, if I look at carbon, 2, 4, 6, We need another electron pair. So we're going to need to share another pair of electrons. So I'm going to take one of the lone pairs, whoops, on the oxygen and move it to a double bond. Okay, that's going to be our Lewis structure. Now, I'm going to go ahead and take a look at my polarity of the bonds. Okay, the carbon-hydrogen bond we consider nonpolar, but carbon and oxygen do have a big enough difference in electronegativity that this is going to be a polar bond. I'm going to go ahead and mark that. Okay. Now, be careful with your geometry. We have only 3 bonding regions around the carbon. Remember, double and triple bonds only count as 1 bonding region. There are 0 lone pairs on the center atom. Even though there are 2 lone pairs on the oxygen, we don't care about that. We only care about the center carbon. Okay, this is going to be trigonal planar for our geometry. Okay, we want to know about those polar bonds. We already designated that. That's the oxygen-carbon bond. Lone pairs on the center atom. Nope, we do not have any. Are these lone pairs or polar bonds symmetric? Okay, the answer to this one is no. Okay, we've got the oxygen on one part of our molecule. We've got hydrogens on the other end. Okay, that is not going to give us a symmetrical distribution of electrons. Whoops, that should be a no, not a yes. Okay, so this is going to give us a polar molecule. Okay, so what we notice here is if the answer to either question of your, well, really it's the symmetric question, right? This is the one that matters, okay? Are lone pairs or polar bonds symmetric? Okay, if the answer to that question is no, that means you have unequal electron distribution and the molecule will be polar overall. Okay, if the answer to the question of bonds, polar bonds and lone pairs being symmetric is yes, then we've got equal electron distribution and the molecule is nonpolar. Okay, so those are 3 examples. This next page has 3 more. Go ahead and take a look at these on your own, and then you can check these with the answer key that will be posted in Canvas. If you have any other questions about Lewis structure, molecular geometry, bond polarity, and this new topic of molecule polarity, please make sure to reach out to your chemistry teacher with those questions, and we will all be happy to help you. Thanks, and have a great rest of your day.